Thereza Paiva from the Federal University of Rio de Janeiro.
Do I speak loud enough? Do I need to use? No? Sorry. Assim? Like that? No, not yet. Is it better? Oh, okay. Now we go. So I want to start by thanking the organizers for having me here. And I will be speaking today about spatial charge and spin correlations in the Fermi-Hubbard model. I am not going to talk about materials, quantum materials, but I hope to show you that cold atom experiments are good enough to give us insight on real materials. So the outline of my talk is I will start talking about ultra-cold atoms and specifically about fermions in optical lattices. And then I'll briefly describe two different works, one in which we observe spin and charge correlations in the 2D Fermi-Hubbard model, and the other one where we study spin imbalance in also the 2D Fermi-Hubbard model. And I will come to some conclusions. So when we talk about ultra-cold gases, we can have different kind of gases. And here I outline the most common used in experiments, lithium, potassium. And the thing is, as these are neutral atoms, we have neutrons and protons. So the number of neutrons is actually very important because this is what determines whether a boson or a fermion. And as we are here interested in interacting fermions and electrons, so we are going to restrict ourselves to looking into what happens to fermions. And the basic difference is outlined here. When we have bosons, we can cool down the system and see them all condensate on the lower state, energy state. And when we have fermions, we have, the Pauli principle here, and we are just having two, as we have like two different species here, 2 atoms per level. So this is very different. And as Raimundo spoke briefly, we usually say spins, but it's not quite true. We don't have spins. We have hyperfine states, and here in potassium, the ones usually used are F9/2, and 2 states here, 7/2 and 9/2, and all the other states are evaporated out of the system so that we only remain with 2 states that we call up and down spins. And on top of having the atoms trapped, we want to have them in an optical lattice. So this optical lattice is formed, has a periodic potential that can be made of counter-propagating lasers, as is sketched here. So we have laser counter-propagating in 1, 2, or 3 dimensions, depending on the experiment we want to make. And when we do so, we generate a standing wave, and the atoms like to sit on the minima of these standing waves. There are other ways of generating a periodic potential, holographic mask, but this is the most used ones. So the idea of using an optical lattice to study a strongly correlated system comes to the control we have in the systems. So as Raimundo also briefly mentioned, the interaction strength between the atoms is controlled by a Feshbach resonance, and we do have control of the strength of the interaction. The lattice hopping can also be controlled. If we make the wells deeper or shallower, we increase or decrease the hopping amplitude, the dimensionality by the number of lasers, the density of how much atoms we keep or evaporate out of the system. spin imbalance, disorder, spin orbit interaction. So we can tailor-make Hamiltonians that are interesting from the materials point of view or the theory point of view itself. And so the idea is using ultra-cold atoms to study many-body physics. I listed here some interesting things that are going on: quantum magnetism, exotic superconductors, disorder, entanglement, and I listed here, you know, all the things that are the topic of this workshop and can also be studied in this framework. So although I am talking about cold atoms in an optical lattice, I am describing the same physics as we do have in materials with strongly correlated electrons. And here it's something that's very important. In these experiments of cold atoms, we have all this control, but the bottleneck is cooling down the system to low enough temperatures to observe the ordered phases. So whenever some experiment is done, what happens first is the temperature is decreased to low enough temperature so the Mott state is observed. And here I placed the cartoon for the high temperature superconductors. And so here we have the antiferromagnetic Mott phase, here some stripe phase, and here the superconducting dome. And if we start from temperatures high up here, as we decrease the temperature, somewhere up here we have a Mott insulator, and then we have to decrease the temperature some more to enter the Niel state. And if we dope and decrease the temperature some more, we enter the superconducting state. So when dealing with this cold atom experiments, we first see the Mott state, and then we see antiferromagnetism, and we have not so far reached low enough temperatures to see superconductivity. But we are around here and looking what happens here. So as we have the same... Sure. So there are some discussion on that, on how you characterize the bad metal. So you could talk to Nandini. She has some very recent theoretical results that will possibly be measured in experiments to characterize the bad metal regime. So here we are going to describe the Hubbard model. That's the one that is, as Raimundo mentioned, the Ising model for strongly correlated systems is the most simple Hamiltonian that can describe correlations. And if for high TC superconductors, it can be viewed as an approximation. In this cold atoms, it's not an approximation. This is what is actually realized in the lab. So here I have drawn a 1D lattice, and we have hopping from one side to the near neighbor site only. And whenever two atoms meet in the same site, they suffer an interaction strength U that can be either positive or attractive or repulsive. Here we are dealing with repulsive attractions, and we do not have atoms with the same spin on the same site. And as I mentioned, we also control the density. So the first cold atom experiment dates from '95, that's many years, and something that's newer and brought a lot of insight to this field is atomic resolution. So it started in 2009 for bosons and more recently for fermions. And this is called what they call quantum gas microscopy. So here is the 2009 sketch from Wasim Bakar for bosons. So here, this tiny thing here, layer below the semisphere here, is where the cold atom is. And here we have a set of lenses and CCD cameras that image the system. And the image they make is this one, which is absolutely beautiful because you see here, this little dots here are actually one atom. And the black part here is empty, and the green is where we have a single atom. So this is 2009. And one thing very important to keep in mind when we look at these pictures is that they do fluorescence to have imaging. And when they do fluorescence, whenever you have a double occupation and you shine light on it, this is ejected from the system. So when you see something like that with an empty center, it's not that it's empty, it's because you have more than one atom and it's been ejected. So what is actually measured here is parity. So if a site is empty or doubly occupied, it shows as empty in the figure, but it's not empty. It could be either empty or doubly occupied. And when we have a lighted thing here, we have a single atom either with spin up or down. So that was 2009, and at 2015, 6 different groups realized that this quantum gas microscopy for fermions. So we have like 3 groups that like to work with potassium and 3 groups that like to work with lithium. And this is 6 years after it was realized for bosons. Sorry. And I will describe here work that has been done with this group from MIT, Zwirline group, and from Princeton, the Packer group as well. And so, as I mentioned, when these experiments are done, the first thing that is done is look at the Mott insulating phase. So here's the Greif's group from Harvard. So they see here, this is the actual image, here is the pixelization, and here is, they had this empty, the hollow system that's actually doubly occupied, and here is for a different density, and we see a single atom per site, which is the Mott insulating phase, and here the same for potassium in Zwirline group. So at the same time, they were able to observe the the Mott insulating state. And now I will talk about systems, 2 studies where we have atomic resolution, and we are looking into antiferromagnetic spin and also charge correlations. So I'll start by describing the collaboration with the Zwirline group, which is done in potassium atoms in 2D, and theory was done in different places. So Esani in San Jose, Nandini in Ohio, and Marcus at Penn State, and me in Rio. And so the idea, once again, is the parity imaging that kicks off whenever we have double occupation. So what's actually measured when we look at a figure like that is what we call the local moment. So either we have a up or a down spin, it doesn't matter, it will show as an atom. And when we have 2 or no atoms, it will show up as empty. So the relevant quantities, the quantities we want to study, are the local moment, because it tells you about how charge is distributed in the system, and the spin, because we want to know, spin-spin correlations and look at antiferromagnetic correlations in the systems. So the spin is just n up minus n down 1/2, and we look at spin-spin correlations with the uncorrelated part subtracted. So some groups develop spin-dependent measurements, and this is done by after you look at the system with both up and down spins in it, you shine a beam of light that ejects only one kind of atom. So here you remove the green atoms, and here you remove the orange atoms. But one thing that has to be in mind, here, for instance, we have a double occupation, and this is here. So when we do the imaging, either when we remove either the up or down, we also remove the double occupation. So this is important to keep in mind. But in doing this, we can remove one species and look at a single species. And with this, and let me give you some definitions. So the density in each site is defined as the density of the up plus the down spins. We have the double occupation and the spins. What is actually measured, as I mentioned, is the local moment, which is the density minus the double occupation, or the density of just one species minus the double occupation. And from this, we can reconstruct and get the spin-spin correlation functions, and that doesn't need to be on near neighbor. It can extend to longer distances. So the experiments were done in Harvard, but here the calculations to go along and provide information on the systems were done either by quantum Monte Carlo, and here is a picture of the cluster we have at UFRJ, and also by numerical Lichen cluster expansions, and these were done by Essan and Marcus Rigol. And the things we calculate here are more or less standard in quantum Monte Carlo calculations, apart from local moment correlations, which involve 8 operators C, and they are hard to code and hard to get statistics that are good enough so we can actually see what's happening at lower temperature. But it's hard, but it's doable, and we just did that. So here is an image of an average between 100 realizations of the cloud, and we see here in the center that the cloud is lighter, meaning it's more full than 1 atom per site, because we have ejected the double occupations, and then we have this ring here where we come close to 1 atom per site. Here it's the charge, the local moment correlations between near neighbors. So if I sit in one site, I look at the 4 neighboring sites and see if the neighbor is also singly occupied or not, and what's the chance for it to happen. And here the spin-spin correlation, if I sit in one side, I look around and see what are the odds that it's occupied. And here for spin-spin correlations, as we expect to be entering an antiferromagnetic phase, it's all red, meaning it's all negative. So all the sites have an atom pointing in the other direction, a neighboring atom in the neighboring direction. And here, just to call your attention, so here where the local moment is maximum is where we have the density at half filling, and here in the center of the cloud that the local moment decreases is we are above half filling, and here at the edge of the cloud we are below half filling until we reach the edge of the cloud. So we are going to look at the spin-spin correlations here at first neighbor distance, the local moment correlation, and we are both looking at it as a function of temperature, fixing at half filling. So the experiments go where the local moment is maximum and look around the neighbors to see what happens, and also as a function of local moment for fixed temperature. And the one thing for theory people like me that is good on these experiments, we don't need to make any assumptions about the shape of the trap. This is something that complicates when we have to average quantities throughout the trap. We have to assume it's parabolic or it's not. And here, as we have on-site information, then we don't need to make any assumptions. So here I have the charge correlation and the spins. I'll break it into 2 parts. Let me show the spin correlation first. So here, this green area is the area between a temperature in units of hopping between 0.89 and 1.22. The dots here, the triangles, are quantum Monte Carlo data, and the lines are numerical Lichen expansion data, which is really reassuring because they are completely different methods and they agree very well. And here, the blue circles are the experimental data. So we see that the experiment is more or less in this range of temperature. And here, as the moment increases, we see a decrease in spin correlations. They get more negative, and this is expected. As we go closer to half filling, we enhance spin-spin correlations, and they become more negative because they become more antiferromagnetic. And here we see that even at U equals 0, which is this dotted line here, the correlations are negative. So we get this Pauli blocking effect. So, as I stressed, we see an increase in spin-spin antiferromagnetic correlations as we go closer to half filling. So this was not unexpected. We already expected the system to go to an antiferromagnetic phase. What was unexpected is what happens to the local moment. So we analyzed the local moment in a site and a local moment in a nearest neighbor site. And what we see is this. So for very small concentrations here, when the local moment is small, the system is empty, we have few atoms, we see an anti-bunching. So the atoms don't like to sit near another atom that has a local moment. And here close to half filling, we see the opposite. We see the bunching of local moments. They like to sit close to each other. And here we have a comparison between experiments and theory, probing longer range correlations. So in the top layer here, we have the local moment correlations, and here the spin-spin correlation. The fact that it becomes red and blue shows that it is here antiferromagnetic. And here, as we decrease the local moment, we are decreasing actually the density, and the correlations, the spin-spin correlations are getting weaker, or if we go the other directions, we see they are getting strong. And we obviously see the same trend in the theory data. And here at the spin-spin correlations, we see this bunching and anti-bunching, as we do see here. So they match pretty well. So for this first part, the conclusions we come is we can detect spin and charge correlations and observe what happens as a function of density. Temperature is not controllable through the experiments. Actually, the experiments need theory to go with so that they can know the temperature they are having. Near half filling, we see this bunching of local moments, and at low densities, on the other hand, we see this anti-bunching of local moments. So now I will turn to this other experiment where we studied a spin imbalanced population. And this was done at Wasim Bakar's group. And also we had theory done at different places, but Ehsan from San Jose, Nandini, and me were the same theory group from the other paper, but now David Huss has joined us. And so these experiments were done in lithium, and we are only concerned at this time with spin-spin correlations. But here, the difference is we have a spin imbalance. So we have here a global polarization, which is the total number of atoms with up spins and down spins. And we define this quantity. And what is done in the experiments is an evaporation of the gas in the presence of a magnetic field, a magnetic gradient. And with this, the evaporation of the different species is done different, and what is left is different. And they can achieve polarizations that go from 0, which is the usual balanced system, until 0.9, which is a very imbalanced population. And although this experiment is not done with a magnetic field, this is done, the magnetic field is just through the evaporation process. The Hamiltonian we are left with is the usual Hubbard model, but in the presence of a Zeeman field that splits up and down spins. They have, it's like as if they have a different chemical potential for the up spins and the down spins. So this is one image of the spin up cloud after the spin down are removed. It's just to give you an idea what it looks like. But, and here is the singles density. So the singles, as I mentioned before, the density after the double occupation is removed, because when you image, you remove the double occupations. So initially, we do have this blue curve where we have ups and down mixed together. Then we do that experiment where we remove one kind and leave only the other, and this is done 50 times in average for each one. So this green line here is the spin up that's left after the spin down is removed, and the red curve is the spin down that is left after the spin up is removed. And a couple of things I'd like to stress here. So this is the radius of this atomic cloud. Here, the radius is of the order of 25 sites. And here, in the central part, less than 10 atoms of radio, we have a fairly flat So we don't have very much varying density, which is good. And here we have more up spins than down spins. We have, in this case, imbalanced case. And here it's also very important. I will refer to this quantity a lot. This is the polarization, the site polarization. So at each site, we see the difference between what's left in the singles up in the singles down. And we see that at the edge of the cloud this changes. But we are going to do the imaging and the measurements in the center of the cloud. So this is theory data only, so that we have an idea. This field here is in units of hopping as well. And here is the non-interacting case, and here the interacting for strong U, which is the U used in experiments. So I forgot to mention, in these experiments, they tend to use U of the order of 8, which is big enough to have strong antiferromagnetic interactions. So here is the polarization as a function of field. And for field of 1 in units of hopping, the system is already all polarized. So this is how the measurements are made. So here we have the case where we removed one species and left the other. But besides that, they do another very interesting thing, which is using a radio frequency pulse to coherently flip all the spins to the plane. So here is measurements are done along the Z direction, which is the direction of the field. And in other cases, they flip the spins, they rotate the spins, and then they measure the spins of the up and down case, but perpendicular to the field. So we call it as perpendicular. So along the Z directions, we will look at the spin-spin correlations that can be obtained in function of the quantities that are actually measured. And perpendicular to Z, we have rotational symmetry between X and Y directions, and we get the perpendicular one. So here's what happens when we increase the polarization. We do see clearly that we start with this beautiful checkerboard pattern that shows antiferromagnetism, and for almost zero polarization, it's the same along and perpendicular to the field. And as we increase the polarization, we see that here the spin-spin correlations are reduced, and they are different. They are more reduced along the Z direction than along the perpendicular direction. And here we do have a sign change along here, these diagonals that we are going to explore a little more. So this is theory only for the X and Z near neighbor correlation. So I take one side and I look at the 4 near neighbor correlations. And here we have the U equals 0. We don't see any difference between X and Z correlations. But when we look at the correlated system, we see that the Z correlation functions is smaller in modulus than the X1. And here, when we look to the next near neighbor, so I look across a diagonal, I see that the Z correlation can become negative. I expected them to be positive, but as the polarization increased, they become negative, and the X is just reduced. So here are theory and experiment together. So the squares here are the experiment data. Here we have the lines are numerical linked cluster expansion. The dots are quantum Monte Carlo. And these lines here that are shifted are the ones where we have not applied the detection efficiency. The efficiency of detections is not 1, it's 0.96. So we have corrected the data to see that. And here we have a band because the experiments I have here. So at 0 polarization, the temperature that best fits the experiments is 0.40 in units of hopping. And the system heats up a little bit as we increase the polarization. We believe that evaporative cooling is not as efficient as we increase the polarization as it is for low temperatures. But the one interesting thing is we clearly have an anisotropy between the z and x direction that we can plot like that, 1 minus z, cz minus c perpendicular. And for zero polarization, we have no anisotropy. For there are regions here where we have something bigger than 1, and this just means one of them is negative and the other is positive, and we do have the anisotropy going to above 1. And we do expect, as we reduce the temperature and increase the temperature we are measuring these correlations, that this anisotropy will go to 1, because we expect the z correlation functions to go to 0 and the x to not go to 0. So when we divide one by the other, this will lead to 1. So this is very interesting because when we have no polarization, we have the balanced system. We have a 2D isotropic antiferromagnetic. We have a SU2 symmetry. And as we are in 2D, TNEL goes to 0. But when we put this in balance, and we do this by having a polarization, we have this canted antiferromagnetism where X in-plane correlations are larger than out of the plane, and we break this SU2 and we are in a U1 symmetry, and then we can have a Kosterlitz transition, and we don't have to go to t equals 0 to see long-range order. So unfortunately, the temperature at which the experiments are done are around here, this 0.4, and this is an expectation for the Kosterlitz transition, which is about 0.15 in units of hopping. In this experiment, which would be 3.3 nanokelvin. So we are not, the experiments are not at low enough temperature to see actual long-range order, but we are close enough so to see some correlations forming. And Rodrigo already told me I'm out of time, but this is quickly. We also look at the polarization as a function of density, keeping a fixed field, and this is very non-monotonic. And we kind of understand what's happening here. When we have no doping, we have an antiferromagnet which has a certain susceptibility. As we dope a little, we have some non-degenerate gas of holes that has a higher susceptibility and then a higher polarization. As we dope some more, we enter the metallic phase, and then we expect the susceptibility to grow. And for the very doped system, it's almost like as if we have free spins that align with the field, and then we have this boost in the susceptibility. So I come to the end. So we do see canted antiferromagnetic in the imbalanced Hubbard model, but we don't see long-range order, but we see orders that are longer than near neighbor forming. We do expect to see a Kosterlitz transition when the experiments are able to reach lower temperatures and reach the Kosterlitz transition, and we do see this non-monotonic polarization with the density, as is also seen in the cuprates. So that's it. Thank you.
Okay, questions?
Very, very beautiful work. I'm very impressed.
Thanks.
I want to ask, in terms of this bunching, which seems intriguing, is this related to a tendency for phase separation that was advocated at low dopings in cuprates, etc.?
Maybe. So, I have like some, I forgot to acknowledge that I was funded by CNPq FAPESG and
Ouch.
the INCT. So maybe I can show you later. I don't know if people are hungry or not, but when we are looking at this bunching and anti-bunching, we looked at 2-point correlations, moment and anti-moment. Anti-moment meaning you don't have a moment, and at a distance r. So, oops, they are out of order here. And so what happens is the moment correlation looks like that. As we increase the local moment, they simply increase, but the anti-moment, they have a minimum, and then they shoot up. And this could be due to doublon-doublon, holon-holon, or doublon-doublon. The experiments are not able to tell the difference, but theory can't, because we can do the calculation separately, and they are actually holon-doublon. So we do see that this bunching is due to holons, and these are holons and doublons being neighboring each other.
Thank you.
I wondered about this KT transition. This transition temperature you found, is that supposedly for a bulk system or for systems the size of, like, what is it, 20 or 30 atoms across?
So that's always a question we have when dealing with that. The Costa-Litalis transition is supposed to take place in 2D and in the thermodynamic limit. So when we have an atom cloud with 25 atoms radio, is it in the thermodynamic limit or is it not? So that's something to be discussed. So there is a paper on Nature from Marcus Greiner. He says he saw 2D antiferromagnetism long-range order, but his cloud was a given size. So long-range is the size of the cloud. Is it true long-range, or? So that's really open to debate. Sorry?
Could you do some sort of finite size scaling with the experiments? So
yeah, so can they do a 25 and a 30 and a 30 and watch what happens? But you know, when you deal with experimentalists, what they see is what they believe. So that's, you know, they think their size is the truth for that system. So it's very hard to convince them, let's do, you know, some finite size scaling analysis. That's, I don't see this happening with these people.
Very beautiful, Thereza. Can they go into the attractive U?
Yes.
And do you expect FFLO phases? What happens in the imbalanced?
So they can. I have seen, even Wasim's group has done the attractive Hubbard model, but not with imbalance. Mm-hmm. And so I don't know what they are waiting for to actually do that, because they could look for the FFLO state. So there are some 1D studies,
yes.
experimental studies
yes.
that have looked for that, but as they have been done a while ago, I don't think there is always this question, have they reached low enough temperatures to enter the ordered phase? And that's the bottleneck, I believe.
Okay.
Any further questions? If not, let's thank Thereza again. And the session is now closed.